All right, so for the rest of chapter 16, it's really going to be all about the idea of spontaneity and making predictions about spontaneity and applying and all sorts of stuff. So we're going to start off just by defining what spontaneity is. So a spontaneous process is one that just happens. So spontaneous means just occurs without external input. So basically this would be a process. This would be a change that you don't need to cause to happen. It just does. Whereas a non-spontaneous process doesn't happen. So for example, example of a spontaneous process would be if you let go of a book, it falls. A non-spontaneous process would be, like the computer you're watching this on isn't going to spontaneously leap up from the desk, right? It's not going to jump on its own. You could lift it, you could make it change, but it's not going to do it on its own. So spontaneous processes just happen. So, the example of falling, once you leave the diving board, you're going straight down, right? And you don't have to say push to go down. If you just let go, it falls, right? You fall. That's just going to passively happen. You don't have to try. Similarly, if you take a drop of food coloring and you put it into water, it's going to spread throughout the water. You don't have to mix it together, right? There's no like stirring or anything. It may take time. This falls pretty quick. It'll take a decent amount of time to eventually have the color spread throughout the water, but it will happen. And it will happen without you needing to mix or to do anything like that. Another example of spontaneous processes is, that if you take, this is a piece of metal here that's very hot, that's why it's glowing. If you put it in this water, which is not hot, the heat will go into the water and the water will warm up. You would have a temperature, you have a temperature difference, and eventually they'd reach the same temperature. Again, that's spontaneous. Now, getting this metal hot initially required some doing. The piece of metal isn't just going to get hot on its own. Instead, you have to do something to it. That would be non-spontaneous. But once it is hot, once you have a hot piece of metal, that heat irradiating or heat flowing from hot to cold, that's spontaneous. You don't have to try to make it happen. And again, non-spontaneous processes can happen. Non-spontaneous processes just require some input, right? Jumping off the diving board would be spontaneous. It is non-spontaneous for this person just to end up on top of the diving board, but they can climb, right? They can climb up to the diving platform. They can do some energy. They can do some input to make it happen. So it's non-spontaneous doesn't mean it can't happen, just that it won't happen without putting in a little bit of effort, right? You got to do something to it. Similarly, a piece of metal isn't just going to get hot. But if you put it into fire, right, you are putting some work in, you're doing some work on it, you're putting that energy in, the piece of metal will get hot. And then it'll spread out heat, spontaneously after it's hot. But, you can make them happen, even though they aren't going to happen on their own, but you can make them happen. So in the context of reactions, a chemical reaction is spontaneous if you mix some reactants and they just turn into products, right? If you think about it in a chemical reaction, all you do is mix the reactants together. You like pour two solutions together, and then all of a sudden they just change into products. The atoms rearrange between the molecules. And so that's an example of a spontaneous reaction, or what it kind of means for a reaction to be spontaneous. So within the context of what we've learned about, a spontaneous reaction is any time that you have a product-favored equilibrium. Okay, so when you have an equilibrium constant, we know that is, that describes, do these reactants turn into these products? So if the equilibrium constant is greater than 1, we call that a spontaneous process. So this is something that we've talked about in specific instances. For example, strong acids have Ka greater than 1, so they fully react with water. When you put a strong acid into water, all of the acid molecules react with water. Soluble salts had a Ksp greater than 1. That means they fully dissolve. When you put that salt into water, it entirely dissolves. The ions will separate out. So it is, of course, important to recognize or remember that in reactant-favored equilibria, some product does form, but not much. We'll at the very end of all this, we'll return to that idea and we can understand why it happens. But a spontaneous process, a lot of it will occur, right? And basically one of the differences is basically, a human doesn't just spontaneously end up on top of a diving board. And you can really understand it because a human is, moles and moles worth of molecules. And so not all of those molecules are going to end up on the diving board. But in the case of a chemical reaction, one molecule changing, you got a decent probability because it's pretty small. But not moles and moles worth of molecules are not changing in these non-spontaneous processes.
Participation 324, question 1. Classify each of the following processes as spontaneous or non-spontaneous. A, NaCl solid becomes Na plus aqueous and Cl minus aqueous. B, water boiling at 25 degrees Celsius. And C, HF aqueous plus H2O liquid yields F minus aqueous and H3O plus aqueous. Ka for that is 7.2 times 10 to the -4. This is the first question on participation 324, due Tuesday, March 24th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the documents where these videos are posted. Again, classify each of the following processes as spontaneous or non-spontaneous. Sodium chloride solid becoming sodium cations and chloride anions. B, water boiling at 25 Celsius. And C, hydrofluoric acid and water reacting to make fluoride and hydronium. Ka for that, 7.2 times 10 to the -4.
So when we talk about spontaneous processes, these are things, when we're talking about chemical reactions especially, these are things that should happen. So a lot of the language that we're going to use are kind of, we talk about spontaneous reactions do just happen. But when we classify a reaction as spontaneous, we don't necessarily imply that it's fast. Our good friend kinetics always comes back and says some of these spontaneous reactions may be really, really slow. The reactions we've talked about before, diamond becoming graphite, steel becoming iron and carbon, all of these reactions are spontaneous, but they have really large activation energy, so they have really slow kinetics. Okay, so slow kinetics can always be modified. You can make these reactions happen. You can get propane to burn in oxygen pretty quickly if you introduce an initial flame. You can all of a sudden get a huge flame, right? But you put in a little bit of flame, and then all of a sudden, boom, you get a really big flame. That's the indication of kind of spontaneous, that a little bit goes a long way to making it happen. You just kind of got to get it started. So that is one kind of the important kind of aspect behind all of the spontaneous processes. We're going to learn to predict whether or not something's spontaneous, and that just implies whether or not it should happen, not whether or not it will happen fast, right? So you may not be able to observe it in the lifetime, in this, over like the lifetime of like the Earth, that kind of time scale, but like in the case of diamond, but they should happen. So the kind of rest of this chapter 16 is going to be focused on kind of the question of what makes a reaction spontaneous. Because really kind of the goal of what we want to be able to do with thermodynamics is the idea of, if I mix these reactants, will I get product? And most importantly, will I get enough product? We know you're always going to get a few product molecules here and there, but will you get a lot of product molecules, and namely enough to be useful? We do chemistry generally we do reactions generally to make products. So will I get enough products? Is this going to be a spontaneous process? So we could kind of think overall through the ideas that we've learned previously from thermodynamics. It's all about energy, and we know that things do tend to go to a lower energy, right? That's why when you let go of a book, it falls. You're lowering the energy. So exothermic reactions do tend to happen, right? We know that in an exothermic reaction, you are releasing energy from the bonds of a reactant. You're making product that is more stable. It's at a lower energy. You're releasing that energy as heat. But endothermic reactions still happen. There are plenty of endothermic reactions that can happen. And if they do happen, if you see a reaction happen, it is spontaneous. Okay? And so that means energy, enthalpy is not the entire story. If we want to predict whether or not a reaction is spontaneous, we need to go beyond just energy. We need to go beyond enthalpy and introduce some new thermodynamic variables that changes in those variables will describe and determine spontaneity, whether or not something actually happens.
First participation question was in this video. Plenty more videos to go, continuing on with chapter 16. See you in the next one.